Alright, so uh, let's get started. It's already 7:03. I hope I am audible to everyone. So, uh, yeah, and let me check my recordings. Okay. Alright, so hello everyone. I welcome you all to this course, Advanced Thermodynamics and Combustion. I will be taking the interaction sessions for this course, and I am first of all I would like to introduce myself. I am Ganesh Kumar. I am a third year PhD student at IIT Gandhinagar. Uh, so uh, I will be conducting this interaction section for this course. Basically, my research work involves uh, computational fluid dynamics and rocket propulsion. So my research works involves uh, predicting propulsion characteristics of a solid propellant rocket motor using advanced computational techniques. So that is what I work in, and this advanced thermodynamics and combustion course is more relevant for my research, and I've studied almost for around 3 years in this field. So basically combustion is more important for me, and thermodynamics is obviously the basic subject, fundamental subject. So uh, that is the reason I'm actually doing this sessions. So if you have any questions, you feel free to unmute yourself, and keep your, like, you can switch on your cameras and you can interact with me. So this is supposed to be interactive sessions. It's not a one-way session. It's not like I will be keep on teaching and you will be keep on listening. Please feel free to switch on your mic and switch on your videos, and you can stop me anytime and ask me questions. Okay. So if you recall what we did in this week, we did 3 modules: temperature and zeroth law of thermodynamics, and first law of thermodynamics, and second law of thermodynamics. This is the first module, so it's just a review of thermodynamics, what we did in thermodynamics course. I hope everyone here have the basics of thermodynamics course. We have 3 people. I think we have 2 people right now. Um, yeah. So have you guys already took thermodynamics course? So you can just type in chat box, or you can unmute yourself and ask. I mean, you can tell. So we have 2 people, Nikhil and Francis. Feel free to switch on your mic and talk to me. Or if you want, you can just type. Have you? So what is your background? Have you guys taken? Are you guys in masters? Are you guys in bachelors? Uh, it would be easy for me to move through the course. We have Nikhil and Francis. Francis, hi Francis. Um, yeah, so actually you joined late. So basically I am the tutor for this course. I will be taking this interaction sessions for the 12 weeks. So do you have any basics of thermodynamics? Have you taken thermodynamics course, basic thermodynamics course? So Nikhil,
Yes, sir.
uh,
So I am passed out. I am preparing for the gate.
sorry, I couldn't hear you. Give me a second. Maybe I will put on my earphones. All right. So can you hear me now?
Yes, sir.
Okay. Yeah, Francis, please go ahead.
I am a pass out, BTech pass, mechanical engineering pass out. I am preparing for the gate.
Okay. All right.
Gate.
Wonderful. And Nikhil, you are in bachelor's which year? Third year. So basically, you both know basics of thermodynamics, right? Uh, So basically, this course is very interesting if you look at it in that way. So because you know basics of thermodynamics, you will go into the you go deeper into advanced thermodynamics, which involves more understanding of thermodynamic concepts like entropy, exergy, and if you go forward, combustion is an important course. If you let's say if you are in automobile field, if you are in aerospace field, if you are interested in gas turbines and rockets, combustion is very important. So basically this course combines, it's like a bridge to thermodynamics to combustion. That's why it's called advanced thermodynamics and combustion. Even though we don't cover full combustion aspects here, but we will give a little bit detail about combustion. And as I said, my research work involves propulsion. So basically, you can feel free to stop me at any time and you can ask me questions. And let's get started for today's topic. Um, I gone through the week one assignments. In week one assignments, the questions are simple, and it is also basics. Uh, so there are only few problems, if I say. There are only few problems which are simple problems, you can easily solve it. So I have today I have 5 problems in front of you to solve, and these 5 problems it's actually tougher than what is being given in your assignment. So you no need to worry. If you are able to solve this, you should be easily able to solve the assignment questions. And today we have 5 questions which is related to basic thermodynamics, and it is also interesting. So I selected all the questions from textbooks. Basically it is from Sengel and Bowles. I hope you all know the thermodynamics book from Sengel and Bowles, and all these questions are from Sengel and Bowles. And I selected these questions to give you more physical insights towards the concepts rather than just solving the question, because that is what is important when we go into an advanced course like this, advanced thermodynamics and combustion. So quickly let's get started. I hope you all gone through week one videos, and if you didn't also, you should be knowing because you all took thermodynamics course. So this week one we did 3 laws of thermodynamics: first law, second law, and zeroth law. Anyway, so the first question we have here is uh, old piston cylinder question which you all know. So what we have here is um, I think we Hamid also joined. Hamid, feel free to unmute your mic and you can ask me questions anytime. I'm just making sure everyone, uh, I'm just making sure that this session is an interactive. Okay. Um, so the first,
So,
yes,
so
Francis. Yes, Francis.
before getting into the question, can I ask a doubt? It's a bit basic question.
Yeah, yeah, sure.
So the first law of thermodynamics can be used for both reversible and irreversible processes.
Process. Francis, I didn't get you. So is the first law of
So
thermodynamics both used for reversible
first
or
law,
irreversible? Is that your question?
yes,
Yeah.
yes, sir.
Okay. So first law of thermodynamics is universal. It doesn't matter whether the process is reversible or irreversible. First of all, first law of thermodynamics is like universal law. It has nothing to do with process or uh, cycle. Okay. First law of thermodynamics, what it states is energy cannot be uh, created or destroyed. So basically, the
Yes, sir.
change in internal energy can be. So there are only 2 ways you can change the internal energy. One is by adding heat, or one is by uh, supplying work, or by removing work. So there are only 2 energy interactions. One is heat and one is work. Okay, and only these two can change the energy of a system. So first law of thermodynamics deals with whether energy is conserved or not. Okay, so may I know, so does that answer your question, or do you have more?
Yes, sir. Yes, so one more question is that the steady flow equation is derived from the first law of the thermodynamics.
Right, right, right. Steady
So
flow energy equation.
then the equations for that turbine, condenser, all that formulas can be used for the any reversible and irreversible. We can
Right.
use it for.
Mhm. Right.
Okay, sir.
So
Okay.
if you look at steady flow energy equation, um, basically what do we tell is it's for an open system, right? If I remember correctly.
Yes, sir.
Right. So in an open system, mass can enter and mass can leave. So the mass of energy entering is equal to the energy enters is equal to energy leaves. That is what steady flow energy equation is. There you need to account for all the energy interactions properly. So let's say so this is for yeah, uh, so if you look at this steady flow energy equation derivation, it's nothing, it's just first law of thermodynamics. There will be mass flow rate in and there will be mass flow rate out, right? And since it's a steady flow, m dot will be equal, and it will enter at h and it will leave at h, some enthalpies. And the reason is we deal here with enthalpy is due to the system is at constant pressure, right? So m dot h1, so there will be q, there will be work in, there will be work out, q in, q out. So m dot h1 plus q is equal to m dot h2 plus W. So this is what you should think. There is only energy in and there is energy out. What are the energy in coming in? Because of mass flow rate, there is some energy in and heat is getting added, so the Q is also getting added. So that is on one side, and that is equal to whatever energy is going on, m dot h2 plus W. So irreversibilities. So if you think of irreversibilities, it has to uh, take part in terms of efficiencies. So steady flow energy equation is valid for both reversible and irreversible process. It has nothing to do with whether the process is reversible or irreversible. But the thing is, if the process is irreversible, the irreversibilities could be due to the friction losses, and because of efficiency losses. Those things you need to take care. That's it. Okay. But steady flow energy
Okay, sir.
is valid for both the process. So it has no. So as I said, steady flow energy equation is like equivalent to first law of thermodynamics. So it is valid for any process.
Okay, so I have one more doubt. So CV equal to R by gamma minus one. There is a formula, isn't it? We can use that formula for any process. I mean, for both irreversible and reversible process. CV. There is a CV and CP formula.
Right.
R by gamma minus one. Gamma R by gamma minus one, isn't it?
Right. Okay, okay. So Cp is gamma R by gamma minus 1 and Cv is equal to R by gamma minus 1, right? So yeah, these are all material properties. It has nothing to do with the process. So yeah, it is for ideal gas. Yeah, given yeah, only when you do ideal gas assumption.
Okay, sir.
Yeah, yeah, true.
So then there is a flow. We take the flow work as negative PDP, VDP, negative integral VDP,
Mm-hmm.
flow work.
Is this the one you are talking?
Yes, sir. Yes, sir.
Okay, what is
So
this?
why we are taking that negative sign? I mean, is it due to we are doing work on the control volume or anything? Is it due to
Okay.
the negative coming from? As I encountered a question that the flow work is taken as given the option negative VDP, and also VDP is also given, and the correct option
So,
is negative
which
VDP.
question you are talking about?
Flow work. I mean, they have asked is the flow work, and they have given the option W equal to VDP, W equal to negative VDP, like that.
Yeah. So which question is it? Where did you encounter?
It's actually a previous year gate question.
I see. Uh, I'm not sure. I don't understand this uh, formula formula yet. Uh, Maybe can you share that question properly so that I can look at it. I'm not sure. So basically, what we do is we write work in terms of PdV, right? So why it should be PdV?
Yes, I will share it. I mean ATVDP.
So if it's a constant volume, there won't.
The negative sign is
Francis, can you hear me?
yes, I can hear you.
Sorry, I missed you. If it's a constant volume, there won't be any work, right?
Yes,
Uh,
sir.
so what was the question again? So if you could share me
Uh,
the correct question, then I would be able to help you.
so I will share in. I need to take it. I will share it.
Yeah, yeah.
Just
So you can take your time. Maybe you can come
can
next week,
continue.
and
You can.
you can come next week, and also you
Okay,
can
sir.
give. Or at the end of this session, if you come across that question, then you can start. Okay.
Okay, sir. I will.
All right. All right. So does anyone have any other questions?
Hello.
Yes, Amit.
Sir, the course starts with the notion of a hydrostatic system.
Mm-hmm.
Normally, we study the simple thermodynamic system, like
Right.
Sanger has noted in the
Right.
book. So, the simple thermodynamic system can be stated to be hydrostatic because we deal with properties when they are uniform, and that defines a thermodynamic state. So,
Right.
pressure will be uniform, and that will
Mm.
make a hydrostatic system. But then again, the properties that were specifically defined for a hydrostatic system were coefficient of expansivity, the bulk modulus, and also the compressibility factor.
Mm.
So, and then we derive the pressure in terms of that. So that is something that I would like to know about, sir. That uh, we normally just know about the ideal gas equation. If it
Mm-hmm.
look at the relation between the state properties, which is definitely limited, of course.
Right.
So if we have a relation of state functions in terms of these properties, it will be more of an independent one. Like it won't. It only depends upon a hydrostatic system, and it can be applied to numerous, like most of the materials. So this is the first question. And other than that, sir, I want to know what reference or what data book can be used for these values for volume expansivity, for bulk modulus, for various gases and solids. I can't find them in the conventional data books.
So you couldn't find them in Sengel and Bowles?
No, sir. I looked at the data books we have for heated mass transfer for like steam tables. They're not given there,
Yeah.
and also in Sage bones I could not find them, sir. Is that are the properties there in Sage bones?
Uh, Probably. I'm also not sure where the property is.
Yes, sir. I checked it. I
I
checked it,
will.
sir. They're not given.
Uh-huh. Okay, then what I would do is I will let you know in the next session where you can find the properties. Coming to your first question, uh,
Yeah.
so the hydrostatic system, so whatever the definitions we derive for hydrostatic systems like isothermal, expansivity, all these are
Mhm.
applicable for thermodynamic system too.
Okay.
What was your specific question? I actually couldn't get your specific question.
Sir, we like using the partial differential equation, like
Mm-hmm.
in terms of writing the variables as partial derivatives. We
Right.
were able to write the change in pressure, the dP, total derivative of pressure, as coefficient of expansivity by, I think it was
Ha
beta
ha
by
ha.
kappa into dt
Right,
for
right.
constant volume process. Sir, I want to know what will be the assumptions for this. I mean to say the limitations for this relation
Okay.
apart from limiting it to a hydrostatic system.
So this one, right? So dP by dt
Yeah, yes, sir.
constant volume
Yes,
is
sir.
beta.
Yeah, yeah, it is.
Uh,
Yeah.
so yeah, there is actually no assumptions till now. So we didn't
Okay.
make assumptions. Did we make any assumptions? So we this is some it can be applied to any equation of state. It no need to be ideal.
Okay.
It no need to be
Mhm.
Walls equation of state, or it no need to be anything. Okay, it is just
Okay, sir.
we can actually have equation of state. It doesn't tell what is that equation of state, and that equation
Mhm.
of state connects state variables p, v, and t. Okay,
Definitely.
that is true, then this function is true, equation of state function is true, and if that is true, this is a mathematical
Yeah.
theory, right? So it is
Yes, sir.
always true, and based on that, we develop this kind of formula. Basically, there
Yes,
is
sir.
no assumption went into it. Only thing is, we say there is only one equation of state uh, which governs that system, right? So maybe you can say simple compressible system or simple incompressible system where there is only this equation of state, and if this equation of state is there, and you can simply write this thing, I believe. So did we make
Okay, sir.
assumptions? I don't think so. We made any
No,
assumptions.
sir. No, sir. We mentioned that we are talking about a simple thermodynamic system. There aren't any electricity magnetic effects,
Hmm.
like we know from
Right.
basic
So,
thermodynamics.
so if that is the case, then yeah. So in that way, we say that there are only three state variables P, V, and T. So there are no
Yeah.
any more state variables, right? So
The independent variables,
so the independent variables are only two, P and V, and
P and V. Yeah.
P and V are P and T, and it is related using the equation of state, which has only P, V, and T. There is no other
Okay, sir.
variables. So if that is the case, then you can define this. So that is the only assumptions. If you think in terms of assumption.
All right, sir. So there is one more thing. I am from a mechanical background.
Okay. Uh, Hamid, actually I couldn't hear you.
Some, from
Sorry.
some thermochemistry
Uh,
to proceed into combustion, to study combustion. So, sir, will it be challenging for someone having a mechanical background
See,
in terms of the thermochemistry involved?
right, right. So can you hear me? Uh,
Yes, sir, I can hear you.
so basically, I'm also a mechanical engineer. I did my bachelor's at
Okay, sir.
uh, uh, so after that, I jumped into aerospace engineering, which involves combustion too. So mechanical engineering,
Okay, sir.
I work with combustions. That shouldn't be a problem. You said something about thermochemistry.
Yes, sir. The chemistry part it has.
So yeah, you no need to worry about it. So it shouldn't be a problem at all. So a lot of mechanical engineers or aerospace engineers work with combustion, and they have a lot of chemistry part. So that comes as a mechanical engineer. So you don't need to worry about it. It should be
So, okay, sir. So one more thing, one final thing.
mhm.
So we will be covering in this course the basics of combustion, or there is
Right.
some like other things as well, like detonation or other.
So, if I go through the course content, I believe we went till laminar flames, diffusion flames, I guess, and it stopped,
Okay, sir.
I guess. So, there are something called heterogeneous combustion, like droplet combustion,
Mhm.
and there are solid combustions, and there are turbulent combustion, multi-phase combustion. Those are advanced topic. Even in
Yes, sir.
combustion courses, you won't be dealing with. Maybe a little bit about
Okay, sir.
evaporation or droplet combustion you might deal with in a pure combustion course, but all these are advanced combustion things which you will not see in any basic combustion course. But in a pure combustion course, what you will have is the same content will be dealt in detail. So in this course, there will it only I believe there are only 8 to 10 lectures allotted to combustion, I feel, I believe. So
Okay, sir.
in a full combustion course, the same content will be taught in a 40 lecture or 40 week, 12-week course, right? So that way they will be covering a lot of content.
Okay, sir.
I mean, content wise same, but it will be dealt in detail. Um, but I think this semester there is only one combustion course, which is Advanced Thermodynamics and Combustion. There is
Yes,
no
sir.
combustion course, right? So maybe in the
Yeah.
next semester there might be some combustion course, so that should be there. But
Okay, sir.
content wise it is same, but it will be dealt in detail and it will be dealt in fundamental way in a pure combustion course. I will try to give you more physical insights when combustion part comes. Um,
Okay, sir.
yeah, we'll discuss more about that later. Okay.
Okay, sir. Thank you.
Okay. So basically, you are in bachelor's or you are a master's student?
Sir, I'm graduated in mechanical.
Oh, okay. All right. All right. Um, all right. Let's quickly finish. I have five problems. I have sixth problem, which is also interesting. But if we have time, we will go through that. Um, so I think this would be very easy for you guys, and you can quickly tell me what should be the answer. So basically, we have the first question. We have a piston cylinder device, uh, which contains 50 kg of water. So if you look at it here, we have 50 kg of water in that piston cylinder device, and it is at pressure 250 kilopascal and 25 degrees Celsius. So basically, when you type here, this degrees go away. Anyway, so 25 degrees Celsius. The cross sectional area of piston is zero point 0.1 meter cube. So maybe we will try to write down what are the givens. So we have pressure, we'll write P1, okay, 250 kilopascals, and temperature is 25 degrees Celsius, and we have water which is 50 kgs, and the area of piston is 0.1, which is given here, okay, and heat is now transferred to the water, causing part of it to evaporate and expand. So uh, this is a piston cylinder, so when you heat it, basically the volume gets expanded, right? So since the piston is freely moving, it will allow, so it will keep the pressure inside the system to be constant. So that is something we need to know. And when the volume reaches 0.2 meter cube, it freely expands and reaches 0.2 meter cube. The piston reaches a linear spring whose spring constant is 100 kilonewton per meter, and then it reaches the spring, okay, and more heat is transferred to the water until piston rises to 20 centimeter and more, okay, and determine the final pressure and temperature work done during the process, and all show the process in kV diagram. This should be simple. So basically we have state 1. So basically this is a thermodynamics, right? So we deal with equilibrium states, okay. We have state 1, which we call it P1, V1 and T1. So this is first state. We have some V1 we need to find, and we are going into some intermediate state where it reaches the spring, right? Just reaches the spring. At that time we have P2, and then we have T2, and then we have V2. It is given in the question that V2 is 0.2 meter cube, right? So 0.2 meter cube, and we will denote it as 1 and we will denote it as 2, okay, and we go from here to here, and in this process we add Q, like some heat is getting added, and then from here we again go to state 3, okay, to P3, T3 and V3, okay, and this is where spring compression happens. Here also we add Q. Now question to you guys, what would be P2? So till so let me write it. Till here the piston is allowed to freely move. Piston freely moves. Freely moves. Okay. So maybe I will write it here. And here the spring is like spring force is getting active. Spring force is also getting active. This person. Now, before we go into calculations, we'll try to first find out whether we know few more state variables, right? So P2 is equal to P1. We have Amit telling P2 is equal to P1. This is because it's a constant pressure process, because piston freely moves. So if there is any change in pressure, the piston adjusts. Okay. And okay, Osho Raja is telling, sir, can you please explain in Hindi? Um, Osho, my Hindi is very bad, but if you talk in Hindi, I can understand. Basically, I'm from Tamil Nadu, where I don't know Hindi, and currently I'm learning Hindi. So, uh, if you want me to explain again, I can explain you. Okay, and you can also talk to me in Hindi. There is no problem. I can understand Hindi. Okay. Um, yeah. All right. So it's a constant pressure process from 1 to 2. So piston is free to move. And how about 2 to 3? Is it a constant pressure process? It's a constant volume process. It's certain that volume changes, because we say the piston moves for another 20 centimeter, right? Maybe we can find volume V3. So what would be V3? It should be V2 plus the distance traveled by piston, displacement of piston or distance traveled by piston, into area, right? So here V2 is 0.2 and displacement is 0. So 20 centimeters 0.2 into 0.1. So I think this is 0.22 meter cube. So this is fine, 0.22 meter cube. How about pressure? Can anyone comment how pressure would be? Will the pressure remain same?
So while the spring is compressing, so the spring force developed will be proportional to the excess in it. So the spring force is changing. So the pressure should be changing, isn't it?
Right. So basically, till state 2, uh, we didn't have any additional force on the piston. So piston is freely moves, or the pressure inside is fully balanced by the weight of the piston, right? So after that, now additional spring force is coming. So that spring force will hinder the motion of the piston. So as Francis said, it is true that the pressure would change, but how much would pressure would change? How do we calculate that? Any idea? So this we can write. P2 is going to be 250 kilopascal, right? So how would be P3? What would be P3? So P3 would be additional spring force acting on it. Need to add a spring force by area to P2. Wonderful. So P2 plus spring force by area. So we all know what is spring force. It is going to be nothing but spring constant times displacement, right? D of piston, you can say. D of piston by area. So the pressure is going to be how much it is? So I think K is 100 kilonewton. Displacement is 0.2 and this is going to be 0.1. So how much is it coming out to be? It is 0.2 by 0.1 is going to be 2 into 100, 200 plus 250, 450, right? 450 kilopascal. So is that clear, everyone? So,
So so
Francis.
so here the we take the deep the distance traveled by the piston as constant is the pressure will be changing at each dx, isn't it? So do we need to integrate anything here? I mean, are we taking the average pressure of k d piston by a?
Yeah. So you think like this. So uh, I understand why you are asking this question. So basically, if you integrate it, what happens is you have to write k into dx, right? And you need to
Yes.
integrate from state 2 to state 3. And when you do it, since k is not a function of x, it would be simply integral of dx. So basically, at the end, you will end up getting k times d piston. So both are equal. One second. So is my screen clear?
Okay, sir. Okay, sir. So by meaning the linear spring constant, you mean that that's why the k is not changing, isn't it?
Yeah, true.
In the
That is
question,
true. Uh-huh. And
okay.
you can think in a different way. See, here we are dealing with states, right? So at the third state, if we have piston and we have a spring force acting on it, and at the third state, what is the force, total force exerted by the piston? If you think that, so there's going to be piston weight plus spring force, right? And if you know for this compression, for 20 centimeter compression, what is the total spring force acting on the piston, then that is the total pressure applied of the system below. So you can even calculate in that way. You no need to necessarily integrate. So basically in thermodynamics we deal with states. We don't care how it moved from state 2 to state 3, but we just care state 2 and state 3 separately. Like I want to move from state 2 to state 3. If I move from state 2 to state 3, what would be my state variables at state 3? Uh, uh, that is the important study here. Okay.
Okay, sir.
All right. So if we do in that way, we found P3. P3 is nothing but 450 kilopascal. So that is known. And we also need to find final temperature. How do we find final temperature? Do anyone have any idea? T3. What is T3? What is this process from 2 to 3? We also don't know temperature at 2. How do we find temperature at 3? And we don't know how much heat is getting added.
So from 1 to 2, it's actually constant volume, constant pressure. So we can use that uh, volume temperature equation
Okay.
for finding the T2.
Okay, so let's say you have T2 value. How do we find T3 value? Shankar is telling PV equal to MRT. We didn't say, yeah, yeah. Water is not an ideal gas. Amit is correct. See, you have to look at the question carefully. You have here piston cylinder containing 50 kg of water, okay, and heat is now transferred to the water, causing part of it to evaporate and expand. So the system contains initially water, and when you start heating, it is at saturation temperature and pressure. So at 250 kilopascal, the saturation temperature probably would be 25 degrees Celsius. I'm not sure. So anyway, if you add heat, what happens is the water is getting evaporated and then expands. Okay, water gets evaporated and the gas expands. Now inside your system you have both liquid and you have both gas. So you cannot simply use ideal gas. You have both water and you have water and water vapor. So how do we do? How do we find temperature? It's a tricky question here. All right. So let's come back to this question later. We'll find temperature soon. Let's find what is the work done during this process. Does that require temperature? I don't think so. It requires temperature. What is the work done? Work done during this entire process. So we have 1 to 2 work done should be straightforward, right? So work done from 1 to 3 is going to be summation of work done from 1 to 2 and 2 to 3. That should be straightforward. So you know what is work done. Work done is nothing but V1 to V2 P times dV, and similarly here also this definition is universal, P times dV. This is true, right? Now we know that this is a constant pressure. This is a constant pressure process. So work done in a constant pressure process is nothing but P times V2 minus V1. Let's do that. And this, we don't know what is this process. We don't know. We don't know this process. We don't know whether it is definitely not adiabatic because you're adding heat. Right? So let's try to find out first work done from 1 to 2. Work done from 1 to 2 is nothing but pressure times V2 minus V1. So can we find V1? We know mass of the water is 50 kg. Initially it is 50 kg water. So what we can take is we can take density to be 1000 kg per meter cube, right? So then volume is volume of water, right? So what density if it is 1000, or you can check the tables and you can reason for constant isobaric process. I'm not sure what you are telling, Mohammed Rama. Reason for constant isobaric process. Okay, I understood. So basically, what you are telling here is the when the volume till the volume reaches, so it causing part to evaporate and expand. So you are allowing the piston to expand. There is no stopper in the piston. There is no restriction to the piston. Piston is allowed to move freely, right? So when there is a small heat addition, it will change the pressure inside the system, and this pressure inside the system is will allow the piston to move, and then makes the system to come back to the old pressure. Okay, I mean it's just piston weight has to be balanced, and piston weight is we don't know piston weight, but the pressure we know 250 kilopascal initially. So if you calculate piston weight, so anyway the system is going to just hold the piston weight, right? So inside that the 250 kilopascal is going to remain same until it reaches state, or until it comes in contact with spring. Okay, so that is the reason from 1 to 2 it's a isobaric process. I mean the piston is freely allowed to move. There is no restriction to the piston. So piston will move until it reaches pressure so that it keeps on having the same pressure. That's it. I hope that's clear. Anyway, how do we find V1?
So,
Yes, Francis.
Actually the work is actually PdV plus VdP, isn't it? So when the pressure is constant, then the work is equal to PdV. Here the state from 2 to 3, both the pressure and volume is changing, isn't it? So can we say that the work is PdV?
Yeah, see,
I mean
work
from the
is. So
yes sir.
we didn't say pressure is constant. Work is generally PdV work.
Yes sir.
It is a universal, or it is the definition of work. Only when there is a change in volume, there will be a work done by the system or work done on the system, right? Or if you say, yeah, so we can simply say integral of PdV is actually work done. It is true for any process. Let's say isobaric, choric, thermal, adiabatic, it doesn't matter. It's just work done is PdV work. That's all. Only thing we are
So,
considering here is it's an assumption that work done into a system there can be only one work done on the system, which is PdV work. The other work done like there can be due to magnetic, there can be something due to electrical. Those work done we are ignoring. So basically we are just dealing with thermodynamic system. So that's why.
so then why are we neglecting that VDP term? I mean, if we work is equal to PV, then during the derivations and all, when we do that dW, we will be getting these two terms, isn't it? So why we are neglecting the VDP term here?
So basic, I think. Yeah, I'm not sure why you were telling there should be VDP also. Because so basically this is what work is. dW is equal to, it is not work is equal to PV. This is not true. Okay. So the true statement is dW is equal to PdV. This is the true statement.
Okay, sir.
Okay. This is the true statement. Because if you, how do you say work? Work is nothing but force times displacement, right? In Newtonian, how do you say force times displacement? The
Yes,
same
sir.
thing is happening over here. Uh, Force is in terms of like F into dx, right? dW is F into dx. We don't say x into df, right? So this and this are
Yes, sir.
similar. Okay. So there is the work is not PV, it's PdV. dW is PdV. That is the work. So that's why when you integrate it, the total work is nothing but integral of PdV. So there
Okay, sir.
no term comes like VDP. That is what I believe. I will check again once more. Why do you say VDP? So these VDP terms comes when there is a entropy and when there is a enthalpy comes in, there will be relations coming on. That's when VDP term comes. Um,
Yes, sir. In the open
for
systems.
now you can think dW is just PdV. The work done is only PdV work. Okay.
Okay, sir.
Hamid is telling quasi-static process is required. Hamid, so what you are trying to say?
Sir, I mean to say that, as you said, that from speaking from the mechanics point of view, work done will always be force into dx.
Hmm.
But when we talk about a process, a normal process, their pressure is not uniform everywhere. So we cannot write work done to be integral of PdV because we don't know the path it follows. If we name the process to be quasi-static, then we know that at every instant thermodynamic equilibrium exists and the pressure is uniform
Uh-huh.
throughout everywhere. Then we
Right,
take
right, right,
work to be equal to integral of PdV.
right. You're right. Ah, that is true. Yeah. So if you, yeah, work is a path function. It is not a state function. That's why we do integration anyway. Um, yeah, you are right. True.
Yes, sir.
No. So how do we find V1? V1 is going to be m by rho, right? So 50 by 1000. Yeah. So how much is V1? I do not have calculator with me. I hope it's 0.05 meter cube. Is it? And pressure is 250 kilopascals into 10 power 3 into V2 is 0.2 minus 0.05 is equal to 250 into 0.15 into 10 power 3. 25 into 1.5. Okay. I'm just telling it's okay. Kg per meter cube instinct. Okay. So that is So it is in kg per meter cube. We need in volume, right? So you need to, I think, see, Amit, I think it's meter cube per kg. Should be specific volume from steam turbine. Yeah, okay. So then if you do it, if you multiply by 50, you will end up getting 0.05. Okay. And how much is the work done for the first state? It's 12, it's 25 plus 12.5, 37.5, I guess. 37.5 kilojoules. Okay. So yeah, this is anyway fine. It's a constant pressure process. How do we find for 2 to 3?
3752.
Uh, can you repeat? Was that Sindhu? I didn't get you. Sindhu. Alright. Anyway, so how do we find for work done from 2 to 3? So we have pressure changing, we have volume changing, and heat is getting added, and we don't know what that process is. Okay, we need P as a function of V. So how do we find it? P as a function of V. So it is true P should be a function of V, but what is that function? Alright. Actually, you already told me what is that function. Can anyone guess what is that function is? Think of it like this. You have reached state 2 where the pressure is 250 kilopascal and volume is zero point 0.2 meter cube. Now you are slowly again adding heat, and what happens is slowly the spring is getting compressed. So let's say the spring is getting compressed for a small infinitesimal length. Okay. So then how do you come up with the relation for pressure? So it's like pressure plus spring force by area. So whatever you told before. So after so the pressure is going to keep on varying when you move from 2 to 3, right? So it is going to be P2 plus spring force by area. But this spring force is also going to keep on varying because it slowly has to compress the what do you say, the spring, right? So it's a linear spring. So for a displacement of 10, the force will be different. For displacement of 20 centimeter, force will be different, right? So then how do you do it? So spring force is K, spring constant is K, and you can write this as, let's say if you write it like this, so I will copy this. Okay. So mm, let's say my piston is here. This is state 2. This is state 1 and this is state 2. Okay, now I will be moving to state 3. So at state 2, let's say for this infinitesimal movement, what you call dx, and from here the difference is from x to dx, right? For this infinitesimal uh, movement of piston, what is the pressure change? P is going to be P2 plus kx dx by a. Or sorry, it will be kx. It's not the whole displacement, it's going to be kx for that. And then from there, so for any now you are writing p as a function of x, it's going to be p2 plus kx by a. Now you just need to write this in terms of function of v. So I hope this is you can understand. It's nothing but whatever you said before, whatever P2 plus spring force by A, but the spring force, it's not K times D piston. Instead it is multiply and divide by area. True. So instead it is the since piston travels through a distance, so instead of D piston, so it goes from 0 to D piston. So here you need to do the integration. So as Amit said, if you just multiply and divide by area, you are going to get P2 times volume by volume. So this will go with P2 times AX divided by, how it will be? V, is it? Multiply by and divide by area. Should it be divided by area? I'm not sure. How it should be? It should be, I guess, displacement, is it? Anyway, actually you don't need to worry about this. You can just simply substitute. Let's see. Work done from 2 to 3 is going to be integral of P2 plus kx by a times dv from V2 to V3, right? So since it's addition, you can just separate these two, V2 V3 plus integral of V2 to V3 kx by a into dv, where dv is nothing but a times dx, right? So this you can write it like P2 is a constant which is not changing, and V3 minus V2, and this you can write it like integral of from 0 to d piston. If you fix that as your it doesn't matter whether you fix or not, but it's going to give you the same results. Anyway, the spring is getting compressed from like state 2, right? So that if you take it as a datum from 0 to d piston, then you can write it like kx dx. So basically you can simply, you no need to think this much, you can simply come up with work done required to compress the spring is nothing but half kx square. So basically here we derived half kx square, so it's going to be plus kx square by 2 from 0 to d piston. I don't know why I'm putting d piston anyway. So P2 times V3 minus V2 plus half K times displacement of a piston, okay, the whole square. So basically if you think this is the work done required to compress the piston, right? So you can even think of it like two, so you can even think of this like this process as two process. One is constant pressure expansion to this place to for a displacement of 20 for 20 centimeter, and then a constant volume heat addition to to compress the spring, right? That also you can do. Basically you end up with, this is the work done to compress the spring, and this is the work done for the change in volume. So if you continue doing this, P2 is 250 kilopascal. Please stop me if you don't understand. Okay. And V3 we all know it's going to be 0.22 minus 0.2 plus half into K is 100 kilonewton 10 power 3 into D piston is.
So can I scroll a little bit up? Okay, so
Basically V2 and V3 is also can be written as A2 times X2 and A times X3. So basically you are just eliminating or you are just cancelling out here. So you can change the integral limits also, or you can even X by A you can change in terms of V, and you can substitute it directly. That should have.
can you explain that once again? That for while defining that pressure term, we didn't use K dx by A. Instead of we write the kx by A, isn't it?
Yeah, so it's for um, okay, so how do I put it? It's yeah, true. It's not k dx. It's kx by a. It's for any state, if you say. So we are going through number of states, right? From V2 to V3. At that particular state, uh, we have spring force which is equal to kx by a. It is not equal to k dx by a.
Okay, so
So dx is small infinitesimal change, and that change comes in this part dv. So dv, how dv changes, it's nothing but area times dx, right? dv,
yes, sir.
dv you can write it like area times dx, right? So similarly you can even completely change this into a times dx, and you can change these volumes. So it will be p2 times a times v2 to v3. What is the displacement? That also you can write it like that. So that's the reason
Okay, sir.
we have something like this. So let's say at 10 centimeter, so total is 20 centimeter. For at 10 centimeter, what would be your pressure? How did you find k times the 10 centimeter divided by, that would be your pressure, right? So that is why I wrote p of x is, p is a function of x, and it can be written as kx per d. All right. So how much is the work done coming into p? I think this part is 5 and this part is right, 0.2 1, and this 2 into 1, can write 2 kilojoules. So it's going to be 7 kilojoules, right? So total work done would be, work done 1 to 2 is 37.5 plus 7, which is going to be 44.5 kilojoules. So only question we left unanswered is T3, right? So only question we left unanswered is T3. 7,000 joules. Okay, right, 7,000 joules, and total is 44.5. True. Thanks, Amit. So what would be your T3? So for finding T3, you no need to know what the process is. Since you already have P3 and V3, you can find T3. But you cannot use any equation of state. But instead, what you can use is you can use steam tables. The reason is here you are adding heat where the water is getting evaporated, right? So evaporated and it expands. So at that pressure, the saturation temperature would be your temperature. The reason is the water and vapor would be saturated and they will be in equilibrium, right? So um, that is the reason the temperature, saturation temperature at 450 kilopascal would be your temperature. Okay. Nothing but T saturation at 450 kilopascal. The reason is we don't know how much water is get or how much water got converted into vapor. We don't know. Uh, uh, we only thing we know is it is in equilibrium. If it is in equilibrium, then the temperature is going to be saturation temperature. It's not going to be any other temperature, right? So
So how can you say that it will be saturation? Can it be inside the dome? I mean, with the dryness fraction.
can it be inside the?
Dome. There is a dome. I mean, with the dryness fraction, uh, the water will be fully converted to the vapor, or
Uh-huh.
will there be some water?
Yeah, yeah. So what is saturation temperature? Saturation temperature means it can be either in it is like equilibrium temperature where both water and vapor can exist, right, at that pressure. So it's not the what do you say? It's not uh, like evaporation point. It's not like freezing point, right? It can be inside the dome, but it will be in uh, the temperature would be saturation inside the dome. Tsat is constant. Yeah, temperature would be constant.
Okay, so
Yeah. So if you look at it, you will understand, or if you simply understand what is saturation temperature, it should be enough.
yes, it will be constant inside the dome. Yes.
Uh-huh. So let's say if you want to draw in a PV diagram, how do you draw all these process? So first is constant pressure. Let's say this it would be constant from this is P1 and P2. Now 1 to 2 is straightforward. From 2 to 3, how does it go? The V also changes, P also changes. The only thing we know is it is a linear function of volume, right? So P is going to linearly vary. Yeah, true. So it is going to be varying like this. And this part will be inside the dome, right? 2, 2, 3. In fact, 1, 2, and 3, everything would be inside the dome. Yeah. So the saturation temperature, that is what the definition is. It is an equilibrium temperature. Okay? So if you look at the tables, you can get the temperature 147.9 degrees Celsius. All right.
So we can get in a conclusion that if both the water and vapor is present, then it will be inside the dome, and the temperature will be saturation temperature.
Right. Yeah. Yeah.
Okay, sir.
Okay. Now we have second question. We already reached 8:10. Anyway, let's try to complete everything. Um, all these are simpler questions. We have a heat pump. It's used to maintain house at constant temperature 23 degrees Celsius. So this is the house where you are maintaining the temperature 23 degrees Celsius. The house is losing heat to the outside air through walls and windows at a rate of this. while energy generated within the house from people, light and appliances amounts 4000. Right? For a COP of 3.2, determine the required power input to the heat pump. So you all know what is heat pump. Let me just quickly draw a conventional heat pump. So there is going to be high temperature, and there is going to be a heat pump which takes some work, right? And then we have T load. So heat is rejected around QL and QH. Alright, TH is 23 degrees Celsius, and outside it is, we don't know what is the temperature at outside. Anyway, and the COP given is 3.2, and what we have to find is what is W in. How do we find? What is given is there is some heat loss, 85,000 kilojoules per hour, and there is also some heat input, 4000 kilojoules per hour, but I don't know how to put these things here. Which one we should put here? What is this 85,000 and 4000? Is it QH? Is it QL? Like, we have coefficient of performance. How can we find required power input? Can anyone guess? Okay, everyone is silent. So, what does heat pump does? Heat pump does it takes the heat from the cold environment and provides the heat into the hot environment, right? So, how much heat it should provide to the hot environment? How do we know that? So, we need to if we need to maintain a certain space at 23 degrees Celsius, we have this home, we need to maintain at 23 degrees Celsius, right? Now, how much heat should I give to maintain that 23 degrees Celsius? That heat should be equal to how much of heat losing it, how much of heat uh, lost, right? So, how much heat I should give to the house is nothing but how much heat it is losing, right? So how much heat it is losing? It is losing 85,000 kilojoules per hour, and but there is also 4,000 kilojoules getting added, right? So we no need to. So anyway, 4,000 kilojoules is going to get added. We don't need to supply it through heat pump, right? It's just a waste of energy if we supply. So the net load on the heat pump is nothing but 81,000 kilojoules per hour. This is the amount of energy we need to give to the house. So this is nothing but this QH, which is 81,000 kilojoules per hour. Okay, I hope this is clear to everyone.
Yes, sir.
Okay. So if you find 81,000 kilojoules per hour is the heat to be supplied, then everything should be straightforward. What is the coefficient of performance of heat?
Desired effect by work done.
Right. Desired output here is, for a heat pump it is going to be QH. This is the amount of heat I am going to give to that this thing, to the house. So work output is so work input is will come in the denominator. So basically you can simply write work in nothing but QH by COP. So how much is the work input you have to give? So this is 81,000 kilojoules per hour divided by 3.2. So work input will be in kilojoules per hour. So what is the work input? So maybe you can convert 81,000 kilojoules, which is nothing but 22.5 kilowatt. So just you need to divide by okay, Amit is giving 25312.5 kilojoules per hour, and I think this can be converted to kilowatt by just dividing 3600. So maybe if you do that, you might end up getting 7.03 kilowatt. You can check this. All right. So only thing you need to identify here is what is this QH, what is the heat load on my heat pump. So how much amount of heat is given by the heat pump is what you need to find. Once you find that, everything will be straightforward. Okay. Um, I hope everything is clear till now.
Yes, sir.
Let's go to third question. Okay. This is also, there is another building. We have a building here whose annual air conditioning load is estimated to be 40,000 kilowatt hour. It's an annual air conditioning load. Okay. In an area where unit cost of electricity is this much, 2 air conditioners are required for building. Air conditioner A has a seasonal average of COP 2.3 and cost to purchase and install is $5,500. An air conditioner B has a COP of 3.6 and cost to purchase and install is 7,000. All else being equal, determine which air conditioner is better to buy. This is actually interesting. So on our first guess, what you think, which air conditioner is better to buy? Air conditioner A has a coefficient of performance 2.3 and air conditioner B has coefficient of performance 3.6. So which you would go for? Air conditioner is nothing but a refrigerator. Okay, no one wants to guess which air conditioner you need to go for. Alright, no problem. We will first try to do it in a systematic way. Let's not guess anything. But if you go by first guess, you would probably say that coefficient of performance in B is very high. So maybe we should go with that, right? Because it will take less work input and gives the same performance, right? So let's see what happens if we do the analysis. Oh, we don't know temperatures, okay, and we know the load. So annual air conditioning load is 40,000 kilowatt hour. So where it should go? It should be QH or QL? QL, okay. Yeah, true. So Amit is right. It should be QL. The reason is it's an air conditioner. You are losing heat to the surrounding, right? So then, if you want, I mean, you are gaining heat from the surrounding, right? So in a sunny day, the heat enters into the house, and you need to remove that heat in order to maintain the same temperature. So we don't know what the temperature is, but this is the amount of heat you need to remove. So this Q load is nothing but QL is nothing but 40,000 kilowatt hour, and we have A and B, okay. And what is the work? So we know COP of refrigerator is nothing but desired output, which is QL divided by W in, right? So we can write W in to be QL by COP of R. So let's write for A and B separately. So what is the work input? for A, it's going to be 40,000 kilowatt hour divided by COP of A is 2.3, and for B the same load but COP is 3.6. What is the work? Can you guys quickly tell what is the work required? 40,000 by 2.3. Alright, I think everyone doesn't have calculator. Oh, nice. Amit. 17,391 and B is 1111.1. Wonderful. Thanks, Amit. So this is it's also in kilowatt hour. Okay. So let's try to find the cost of this. So we know 1 kilowatt hour is nothing but how much is it? The cost is 0.1, I think it's dollar per kilowatt hour. So what would be the cost here? It's going to be 1739 and here it's going to be 111. Okay, so this is just the what do you say, energy, so amount of electricity cost it's coming up, right? But you need to think in terms of installation also. So you have installed the the air conditioner A is $5,500, right? Installation cost, it's nothing but $5,500, and installation and procurement and installation cost of this is $7,000. So if you calculate in terms of this is per year. This is also per year. So because all these are annual load, right? So this is annual. So if you're just going to use that air conditioner for a year, you should, in terms of money, you should go with this, right? And but if you go with this, yeah, if you are using it, let's say for 2 years, then also I think probably this would be better. For 3 years, maybe at 3 or 4 years, if you are continually using, then B would be better. If not, A would be better. Anyway, it's your decision to make. You can decide it. But the important thing is you can calculate this in like this. Okay. All right. Let's go with fourth question. I hope everything is clear till now. So what is the fourth question? We have Carnot heat pump. Okay, we have a Carnot cycle here. So we have a Carnot heat pump. It's used to heat the house and maintain at 25 degrees Celsius in winter. On a day, so there is a heat pump. There is a heat pump. On a day, when average outdoor temperature remains at 2 degrees, the house is estimated to lose a heat of 55,000 kilojoules per hour. If the heat pump consumes 4.8 kilowatt of power while operating, determine how long a heat pump ran on that day. The total heating cost, assuming an average price of this for electricity, the heating cost for the same day if the resistant heating is used instead of heat pump. So they are telling we have a heat pump and we have a work input, and yeah, okay. So we have QH and we have QL, right? So this QH, what this QH should be? It should be the amount of heat it lost, right? So it should be 55,000 kilojoules per hour. So they are telling it is operated. How long the heat pump ran on that day? They are asking how long the heat pump ran on the day. So for that we need to find out. Yeah, okay. How do we find out? Maybe you can tell me why the time concept is coming here. So in a day, how much uh, heat? What is the heat load for heat pump, or how much heat lost by the house? You can calculate that in a day. It's going to be 55,000 into 24, right? Okay, so this much amount of heat I have to remove. Okay, 132,000 kilojoules, right? This much amount of heat in a day I have to remove, and uh, so what else we have? And it's a Carnot heat pump, so we can easily find COP of heat pump. What is the COP of heat pump? I'm just trying to understand what should be my work in, right? So anyway, to the heat pump, I'm is operating at 48 kilowatt, but I am just understanding what should be my work input for this heat pump. So what is Carnot heat pump's coefficient of performance? It's going to be QH by work in, I believe, right? So QH by work in is nothing but QH minus QL, and it is going to be TH by TH minus TL. So for a Carnot cycle, you can write Q as a T, right? So okay, Amit found out the coefficient of performance. It's nothing but 12.957. So this coefficient of performance of heat pump is nothing. It's what the this is the coefficient of performance for this heat pump. Now I have a heat load of this much. Now let's try to find out working. How much power I require, or how much energy I require, which is nothing but QH by 12.957. So I know the heat load, which is 32,000, some 132 four zeros divided by 12.957. This much amount of work I require, and my heat pump input is 4.8 kilowatt, right? So if the power input is 4.8 kilowatt is nothing but kilojoules per second, or energy per unit time, right? So then you can find the time, how much time I should run the heat. What happens? What is the working? So is that working? Okay, 101,875.43 kilojoules. Alright, so this is the kilojoules, and we know that W dot in. The reason I use W dot is it's written in terms of kilowatt, it's on power, right? So till now we didn't use that, but when you have two things, you can change it accordingly. So it's nothing but this is nothing but W in divided by T. So you can rewrite this as T is equal to W in by W dot in, which is nothing but 101,875.43 divided by W dot in is 4.8 kilowatt. So this is also in kilojoules, so kilo will get cancelled. So how much is this coming? So maybe if you write, it might be some seconds, some amount of seconds, maybe you can write in hours. Okay, 5.896 hours. So you need to run for 5.896 hours to get for the in a day. In a day, you need to run the heat pump for 4, like you can run for 5.896 hours. So, what is the total heating cost, assuming average price of this much? So, what would be the total heating cost? So, if you use heat pump, this is the amount of work you are giving to the um, like the amount of work you giving to the heat pump is what goes into the electricity charges, right? So it is going to be W dot in into number of hours, T in hours, times the cost for hour, which is nothing but 4.8 into 10 to the power 3 into 5.896. Okay, this is, so they might be writing in terms of kilowatt, so you can ignore this. 5.896. This will be in kilowatt, this will be in hour, kilowatt hour, into how many dollars? 0.115 kilowatt. So it gets cancelled. So total this much amount of dollar. How much it will be? Might be some $3, some probably 3.113 dollars. Now the reason for us to find this is to appreciate this concept of heat pump. The heating cost for the same day if resistant heating is used instead of heat pump. Let's say you do resistant heating. What is resistant heating? You will just heat by sending current, right? So what is the heat? So what would be the resistant heating cost? How do you find out? So for that you need to find how much energy or how much power required for resistant heating. Power for resistant heating. What is the power for resistant heating here? You are not having heat pump, so you have to provide all the heat load using this resistant heating. So basically you need to provide around 132 how much is that 13 lakh 20,000 kilojoules. So the power is going to be 13 lakh 20,000 kilojoules per day, right? uh, how do we convert into hours? Into 1 kilowatt hour, which is nothing but 36,000 kilojoules, right? So you get kilojoules, then you can, yeah, this is the total power. And if you want to find the cost of resistant heating, you can write 132,000 into dollar point. So this is going to be very high compared to uh, the heat pump. That is the reason it's better to use heat pump instead of a resistant heating. How much it would come? It's probably greater than so basically you are supplying all the heat load through resistant heating. So that's why you'll be having you have to supply 13 lakh 20,000 kilojoules of energy. All right. So is this clear? I think I rushed a little bit. So what is the value you are getting for resistant heat pump? Sorry, resistant heating.
40.3, sir.
Oh, all right. Thank you. It's around $40.3. So
Yes.
you can compare it with $3, right? So compared to $3, $40.3 is too much. So for in a day you will be spending $40 for if you are using resistive heating. If you use heat pump, it's going to be lesser. So that is the reason. But anyway, this is a Carnot heat pump, and also it's like reversible engine. So this this coefficient of performance would be even lesser for a heat pump like normal heat pump, and we also have temperatures in 25 and 22, so the coefficient of performance will be even less. So when you consider that, you have to check what would be your power. Okay, all right. Thanks for the solution. Now we have one more final question here. Inventor claims to have designed cyclic engine for use in space vehicles that operates with a nuclear fuel generated energy source whose temperature is 920 Rankine and the sink is 490 Rankine that radiates waste heat into deep space. He also claims that this engine produces 4.5 horsepower while rejecting heat at a rate of 15,000 BTU per hour. Is this claim valid? So why they are asking is this claim is valid or not? Anyway, I converted all these things into SI units for easier for for easy to easily calculate. So they are asking whether this claim is valid or not. So what he did is the inventor he designed a new engine, heat engine, to use in space vehicles. He designed it for space vehicles, which has a nuclear fuel generated energy source whose temperature is 920. So there is a um, energy source which you can see it as a reservoir, hot reservoir at 920 Rankine, and there is a sink also at 490 Rankine, and it is a cyclic engine, and it also produces energy. So uh, in terms of thermodynamics point of view, everything is there. Like there is a like energy, it takes energy from a hot reservoir and release it to a cold reservoir, and while doing so it does some work also. So as per second law of thermodynamics, it should be valid, like if you just vaguely see. But what we also know is there is something called Carnot efficiency or reversible heat engine efficiency. Only when this efficiency is less than that reversible heat engine efficiency, then only you can say that this engine is valid. If not, its claim is wrong. Okay. So for that we need to find what is the Carnot efficiency. So what would be the Carnot efficiency for this heat engine? This heat engine is efficiency is nothing but Q input, Q dot H by work output, right? Or is it opposite? It's opposite. Yes. Work output. H, right? So Q dot H is nothing but Q dot H minus Q dot L divided by Q dot H, and if it's a Carnot you can simply write TH minus TL by TH. This you can write it as 1 minus TL by TH. Okay, so I converted everything to Kelvin scale, which you can write it like 272 by 511, and you can find this efficiency. And the next is the real engine efficiency, which is work output by Q dot H, and work output is given 3.36 kilowatt divided by Q dot H. Q dot H is going to be, we know that work output is going to be Q H minus QL, right? So this QH can be written as work output plus QL. So work output is 3.36 plus QL is 4.395. So now you can find the efficiency of this also. So what is the efficiency you are getting for these two engines?
Carnot efficiency is 46%.
Okay, 46%. And real engine efficiency?
1 minute, sir. It is 43%.
Okay, 43 percentage. Yeah. So anyway, this is less than Carnot.
Yeah.
So it is valid. So you no need to worry about it. So whatever this guy proposes is correct. Anyway. So thanks Hamid. Thanks Sindhu. So here uh,
So
yes
490
Francis.
R is
Yes Francis.
so how that 490 R is converted to 272
Okay, so
490.
there is a conversion scale. I believe it is 5 by 9 or 9 by 5 something. So you can search that in Google. Rankine to Kelvin. So you can just put it 420, 490, 272 Kelvin. So it's just you need to
Okay, sir.
0.555 something.
Yes, sir.
Okay. So it is also another scale, just temperature scale. So if
So,
so anyway, if
like
it, yes, Francis.
for that third question, there was a for you said that for 2 years and 3 years we can decide for that uh,
Mm-hmm.
refrigerator. I mean heat pump problem.
Mm-hmm.
So we will be if it is asked for an exam, then how we will decide whether we will be buying a refrigerator for about 5 to 6 years, isn't it? So how we will decide the
All right. So in exam, most probably the question would be clear. Here it is little bit vague. We don't know how much time they are going to use. Is it for 1 year they are saying which one is better for 3 years or for 5 years? We don't know how much is it. In exam, question would be more clear. So you don't need to worry about it. But basically this is to show you probably in exams they might not even ask such kind of questions. This is to show you the difference, just for your information. In exam the questions would be even more fundamental, testing your knowledge. Just it might stop till here, just finding work input. That's it. They no need to, they may not ask the cost, energy cost and other costs. Okay.
okay.
So actually I have one more question, but you can try it on your own. I will upload this PDF also. Uh, so this question is also interesting. So basically it is actually recommended, if you have a hot food, you just first cool it down to room temperature and then keep it inside a refrigerator. Okay. But why it is recommended? What if you don't do it? What is the amount of energy? What is the amount of work required by the refrigerator? What is the additional amount of work required by the refrigerator? And because of that, how much cost you are going to gain? So that is what this question tells. This question, I mean, talks about. It is so if you look at it, it is commonly recommended that hot foods be cooled first to room temperature by simply waiting a while before they are put in a refrigerator to save energy. Despite this common sense recommendation, a person keeps cooking a large pan of stew 3 times a week and putting the pan in a refrigerator while it is still hot. So there is some guy who lacks this knowledge. He he cooks it and he just puts in the refrigerator while it is still hot. Okay, thinking of money saved is not probably too, it's probably too little, that's what he thinks. But if you do this calculation, you can show him that the money is significant. So for that you can do this calculation and you can convince him. This is actually kind of funny problem which you can do it when you are free. So it it gives you a few insights like how much you can save. Until you calculate it properly, you will never know how much you would be saving. Right? You might think it is little, but it would be more considerable amount. So that is something you can do it on your own. Okay, and yeah, I think that's it. All right. So so this is a review of basic thermodynamics. So the questions are little simpler. As we go into the course, you will be having more complicated or more challenging problems which you will come across. All right. So if you have any questions, you can ask me right now. I will be here for.
So, I got that question. Can I present that question?
Haha, yeah, sure. So you like to present it?
Yes, sir.
Okay, let me unpresent. Stop sharing. Okay. Now you can present it.
So, one
Let,
minute.
let me enable it.
So, can you see?
Yes, Francis.
So, this was the question.
Okay, which one of the following expresses the reversible work done by the system? Okay, between states 1 and
The
2.
answer was given this.
I see. Integral of 1 to 2 ED. This is work done by system state between states 1.
So, and also in the Sengelin balls, they have reversible steady flow. They have shown that it will be negative EDP, but at this portion they said that we can avoid this negative sign. So like it is not that mandatory. Like, but the solution is actually negative EDP.
I see. Okay. Hmm. All right. So maybe I will look into it. Which in Central and Goals, where do you get?
It's in chapter 4, chapter 7, steady flow, reversible steady flow work.
Chapter 7. Okay. Okay. Okay, there is
Like
some
they are
manipulation. Yeah, yeah, I understood. So, So there is yeah, okay. Reversible is 1 to 2 VDP. Check connecting energy and potential energies are negligible. The equation reduces to 1 to 2 VDP. Yeah. Okay, they are using manipulations to get that. Okay, but basically for a closed system, it's just PDV. For a steady flow energy, they are using first law of thermodynamics, and then they are substituting the relation for del Q is TdS and TdS is dH minus dP. Probably we will cover these topics soon in coming lectures, I feel. I will go through this once and I will let you know. So your confusion is whether it is minus VDP or is it plus VDP? Is that
Yes, sir.
okay? All right. I will let you know maybe next session. Okay.
Sir, also this VDP will be only used in the open system. If for that piston cylinder work, we don't need to consider anything like this. We
No,
only
no.
need to consider PDV work. Isn't it?
So yeah, actually there is only one word for a closed system. It's nothing but integral of PDV. There is nothing else. Okay. So what they are trying to do is they are trying to modify the equation. They cannot get the work for reversible process like straightforward like PDV, right? For a closed system it's just PDV. For an open system the volume does not change, right? But still we give some work to the system. Right? Can you understand what I'm trying to say? So if you have a closed system, there is a volume change. Because of that, you are doing some work, or by doing work, there is some volume change, right? So there is only one work, which is a PDV work for a closed system. But in an open system, it's not that straightforward. Even if you do work, there is no such volume change because mass is continuously entering and leaving. So we should somehow get a relation for change in work for a reversible open system like steady flow system. So for that, they are using certain relations, and that's how you end up getting VDP. Okay. So I think it should be negative VDP because it's always
Somewhere I see that is it due to that we are doing work on the control system. Like if there is a control system, the fluid is going in and out, and in order for the fluid to move in, are we doing the work on the control volume? Is it like anything like that?
no. So okay. So let's take an example. If you take an example of compressor, okay, the volume is same, but the pressure changes from inlet to outlet. To operate a compressor, you need to give some work, right?
Yes.
So in a compressor, what happens? The pressure changes from low pressure to high pressure,
Yes, sir.
right? So if it changes from, so you can, okay, let me share it.
Also, for compressor also we will be using that steady flow equation, and we are getting the work is equal to h1 minus h2, that equation, isn't it?
Right. So, so if you take a compressor, for example, let's say, so what happens here? There is P1 and there is P2, right? So it's a steady flow, and you give some work in, right? So if you, so work is given to the system, so it should be positive, right? But if you look at it in a compressor, if you just put VDP from 1 to 2, okay, then what happens? V times P2 minus P1. So I think I wrote a turbine. Right, right. This is compressor, right? This is one, this is two, and you are giving work in, right? So what they say is they are telling W work reversible is nothing but minus integral of VDP, right? Plus some energies, Ke plus potential energies, right? From 1 to 2. Is that what they say? Is that the relation?
Yes, sir.
Yeah. So here, if you, let's say if you ignore the kinetic energy and potential energy time like terms, what happens if you just use this? Volume is same, but pressure changes from P2 minus P1. So P2 is greater than P1, right? So this whole term would be positive, but you are doing work on the system, right? So
Yes, sir.
the convention is the work done on the system should be negative, right? That is the convention.
Yes, sir.
So if you go in that way, this should be the answer for it. Then only it becomes negative, right? So if it is integral of VdP from 1 to 2, then this whole term becomes positive. Work done. Work done, if you consider this whole term becomes positive. Positive means work is done by the system. But in compressor, you are doing the like you are giving work as a input. Work is done on the system.
Yes, sir.
Probably, I think this should be the correct answer. That is the reason you should use this. So basically, that's the universal convention we use everywhere, and the probably the motive of asking that question is also, if you change the convention, this is also right. It's not like this is completely wrong. It's just we don't know what convention they followed when they asked that question. So this is the universal convention like most of the people follow, and that is the reason they might have taken it for granted that this is the convention you should use, and if you use that convention, this is the answer you should get. Is that what the answer they gave?
Yes, sir. Negative dB.
Okay. But how do you get this relation? I will let you know in the next class. Basically, but work is nothing but PD. Talking about PD.
Okay, sir.
Okay, and basic for a, this is for a closed system. If it's an open system, then we don't know how to get the work. So we use first law of thermodynamics and then this TDS relations to get the to get this kind of expression. So I will let you know that in the next class.
Okay, sir.
All right, Francis. Thank you.
Thanks, sir.
Let's meet in the next class. Okay.
Thank you, sir.